Hello, class. Welcome to Chapter 3. We look here at probability. And as you know, probability is the likelihood of something happening. So it is what surrounds us. And we often think, what is the chance that it's going to rain today? Or, the flights to LA, Los Angeles are always late. I wonder if I should expect my LA flight to be on time today. So we have these kind of questions, and we constantly compare what we know of an event occurring to inform our expectations of how it will occur in future. And so for this, we use mathematical backing to solve these probability problems. So let's start with experiment. I'm trying to provide definitions for some terminology here. So experiment would be a planned operation that is carried out under controlled conditions, because it's a planned one, right? So we control the conditions. And an example would be flipping a coin twice. Okay? You know how famous this example is, but in stats. So we'll go with the traditional example then. So then we have something called trial, experiment and trial. Now, trial is one repetition or instance of an experiment. Okay. So let's say in the above example, if flipping a coin twice is an experiment, this experiment, if it's repeated 3 times, okay, repeat the experiment of flipping. My pen went flipping. Repeat the experiment of flipping a coin twice. Put that in parentheses. 3 times. Okay. So what we see here is that in each trial, you flip a coin 2 times. This implies, this arrow with two lines and an arrow wings implies. This implies that there are 3 trials. So I hope that explains to you what the difference is between a trial and an experiment. And then we have outcomes, of course. So the outcome of an experiment in probability is that any of the possible results can come out of it, right? So it is a collection of all possible results. So in flipping a coin example, if we flipped it once, right, there are 2 possibilities, 2 outcomes, 2 results. You can either get a heads or a tails. So we abbreviate it as H and T. Okay. So when you flip it twice, then we'll see how that works. So let me just give you a basic example of flipping a coin once. Implies that you get 2 outcomes, head and tail, right? These are the 2 possibilities. There are no other possibilities outside these 2. But when you flip a coin twice, so flipping a coin twice is that you flip it once, and you might get a head or a tail, and flip it the second time, you get a head or a tail. So you are having 2 layers. So it's going to look a little more complicated, but these are the possible combinations, okay? That you flip the coin first time and you got a head. The second time also you got a head. The first time was a head, the second time was a tail. The first time was a tail, the second time was a head. First time was a tail, the second time also was a tail. You see that? So you have, and so if you're flipping it 3 times, then you'll have HHH, HHT, and you have those many outcomes there. All right? So we will take a look at an example and just see if we can understand the experiment, trial, and outcome from that example. mutual friends sit down together to study in the library. One of the friends is a nursing major and one of the friends is a business major. You choose one of the friends at random to receive a free coffee from the library cafe. So A, describe the experiment in words. B, how many trials does this experiment have? And C, what are all the possible outcomes of this experiment? Okay. So think of the experiment. The experiment is there are two friends seated there and you get to choose one of them at random. So the experiment is choosing a friend at random. I'll just write experiment first. Okay. So what is the trial? How many trials do we have? The experiment is repeated only once, right? So you can safely say that your trial is also 1 in this experiment because of this. So trial equals 1. There's only one trial in this experiment. And for C, in terms of outcomes, the outcomes would mean all the possible results here, right? So what are the results? The results are that you might choose a friend who is a nursing major or a business major, because those are the only two possibilities, right? So you're going to choose this person at random, so we don't know which one it will be. So the possible outcomes are nursing major and business major, right? We can extend this idea, right, into further definitions of, events and sample space. So we can say, well, a sample space is a set of all possible outcomes. Okay, outcomes are all possible results, and if you have a set of all possible outcomes of an experiment, then that would become your sample space. Okay, set of all possible outcomes of an experiment. So we use the word set, and in math, set has its own meaning. Meaning you will write your collection in curly brackets. That's how sets are written. So if you're flipping a coin once, the two possible outcomes are heads and tails. So this is how you will list it: H, T in curly brackets. So this becomes your sample space for flipping a coin once. So these are the possible outcomes here. Okay. If you go to the other example we did, flipping a coin twice, this would become the sample space. Okay. The sample space is the collection of all, or the set of all possible outcomes. Then we have events. So event is a subset of the sample space. It's a sub-collection, right? Subset of the sample space. Sometimes we write sample space as SS. All right. Or in some ways, you're grouping this. So we usually use capital letters to denote events, etc. And say, for example, if we say an event of flipping a coin would be flipping our heads, then you are saying that your event A is flipping a coin and getting a head. Okay, so I would say A is, you're describing basically what outcome or what a subset of the sample space you're interested in. So flipping a coin and getting a head would be A, right? So that is a subset. So only H would be in your event. So event A would be just the H, because that's the only outcome you can expect here, right? Now we talk about the probability itself. So you say, what is the chance of getting ahead when I flip a coin? So if you were to ask that question, you're interested in the question, then we intuitively say, well, there's only one head you can get, and there are two possibilities. You can go head or tail. So you say it's a 50% chance that you'll get ahead. We get this understanding intuitively, but I'm going to structure this for you, statistically. So probability is a measure. Measure means some numerical quantity in this case, right? Measure of a particular event happening compared to all events in a sample space. So we usually denote it as P of A, meaning in this case, let's use the A description from the previous definition, event A. This would mean probability of event A. So what is the chance that event A happens? That's the question. So here you can think of the probability of event A is the measure of a particular event happening. So you want one head, right, to all events in a sample space. So there is only one element here. So there's only one element, right? One count here. And here you have two. So there is only 1 out of 2 that you can expect, right? So that's going to be 1 out of 2. So you can either write it as a fraction like this, or as a decimal, or as a percentage, 50%. This is what we got intuitively, but we are trying to describe it to you as the number of results or outcomes from event A divided by the total number of outcomes in the sample space. So we had one event in A, and we had one outcome in A and two outcomes in sample space. So we got this. And remember that probabilities are always between 0 and 1 inclusive. Always lies between 0 and 1, both inclusive. I'll give you an idea. 0 and 1 are plain numbers, but if you converted them to percentage, 0 converts to 0%, and 1 converts to 100%. We know how we change it to percentage, right? Multiply by 100%. And so if you think of it as a number line, okay, where we have 0 here and 1 here, this is 0.5 right in the middle. So this is basically 0%, this is 50%, and 1%, 100% for 1. What we're saying is, if you're talking about a chance of something happening, 0 indicates no chance, no way that it can happen. And 100% would mean that absolutely it will happen, certainly. Okay? I'll just say certainly. So there is no ambiguity there. You know absolutely that's going to happen. So 0 is no chance, certain is 100%. So in between, 50% is, we're not quite sure. So the more you hover in this region, it's an unlikely situation. Unlikely. The more you hover in this area, if your values are 0.7, 0.9, that is more likely that the event will happen. So you cannot have negative probability because it makes no sense to have negative percentage. You can't have anything more than 100% because 100% means it's all of it. So how can you go beyond it? How can you exceed that? That's the reason why your probability always lies between 0 and 1. So the way we describe it is A, not necessarily this particular example A event where we're talking about getting ahead. any event A, this is how we will write. This means there is no chance that that event A can occur. That's what this means. Okay? This means that event A can never happen. So understand that we are writing it all in mathematical notation, so it has to be crisp. We can't have it written in words. So P of A equals 0 is a crisp way of saying that event A can never happen. If I say P of A equals 1, it means that event A always happens. And we just saw that if we had it as 0.5, you can say that event A is equally likely to occur or not to occur. Right? Because that's what we mean by 50-50 chance. So that's how we kind of describe sample space and probability. Let's take a look at an example. So if you look at this example, a fair coin is flipped twice. The sample space, describe the sample space, the event A of getting a heads on the second coin flip, the probability of A denoted by P of A, and the likelihood of A given P of A. So let's start off with A, sample space. We discussed this before, so it's sort of going to be a little easy here. So we're flipping the coin twice. So the first time we flip it, we might get a head. Second time also a head and then a tail, or a tail and then a head, or a tail and a tail, right? So we have 4 outcomes. B, A is given to be the event. Because I write capital A, I don't have to say event A because I write it as using the notation. So A is getting a heads on the second coin flip. So you're looking at the second position, okay, the second position to see where there is a head. Okay, so then you come back here and then you define your A to be HH and TH. Okay, you're only focusing on the second coin flip and focusing particularly for the looking for the head. All right, so we have 2 outcomes here. C, it says find the probability of A denoted by P of A. So P of A is probability of A. Probability of A, as per the definition, is the number of outcomes in the desired event divided by number of outcomes that are totally out there. That is your sample space. This is intuitive, right? This is how you can think about this. So then you have 2 outcomes from event A out of the 4 outcomes in the sample space, which comes back as half. So again, you can leave it as a half or 0.5 or 50%. What was D? D was the likelihood of A. Okay. So we got P of A to be half, which is right in the middle. It's neither close to 0, which means it's unlikely, nor close to 1, which means it's more likely. It's right in the middle, exactly in the middle. So then all you can say is you can conclude by saying that event A, so you don't have to repeat the entire event. If you want, you could, meaning you can say getting a heads on the second coin flip is equally likely to occur or not to occur. Event A, getting head on second coin flip. is equally likely to occur. Notice the language there, right? Or not to occur. Let's take a look at tree diagrams. As the name says, it's a diagram. It's some kind of a graph. It's a special type of graph that will help you to visually determine the outcomes of an experiment. It helps determine the outcomes of an experiment. It's called a tree diagram because it's got branches and it looks like the tree, or branches of a tree, branches off. So it just makes it more visually appealing, and it makes it easier to solve the problem. Okay. So here comes our example. Here is a delicious problem. So an ice cream parlor claims to have more than 14 possible sundaes, and their slogan is, "Try a new one every day for 2 weeks." Two brothers visit the shop to test out this claim. They are presented with the following menu. For each sundae, a customer is allowed to choose the number of scoops, one flavor of ice cream, and one topping. The brothers quickly map out all the possibilities for a sundae using a tree diagram. How many possibilities are there for a sundae? All right. Well, you have it in a chart form and a tabular form, but it's kind of hard to see all the combinations that are possible because the chart is pretty, it's well summarized that you really can't see the full extent of it. So this is where we make use of the tree diagram. Okay. So what we're going to do is we're going to start off with the three, the three possibilities that we have at hand. So let's take the number of scoops. Okay. So then that will be, you can choose one scoop or two. Okay, I'm trying to draw a tree diagram, so I need to space it out. Okay. And next we have ice cream types, right? Well, flavors. For sake of space, I'm going to write them in shortcut. So we have vanilla, chocolate, strawberry. So if you choose one scoop, you still have the choice of these three flavors. Likewise, if you go with 2 scoops, you can have 2 scoops of vanilla, chocolate, strawberry. Okay. And then the third option is that you get to choose toppings, one topping, right? So let's write toppings. So remember again, a customer is allowed to choose the number of scoops, one flavor of the ice cream, and one topping. Okay, let's keep that in mind. So, in vanilla, we can have rainbow sprinkles or fudge sauce. Chocolate, same thing, rainbow sprinkles of fudge sauce. And if you went with 2 scoops, there again, right, because that was your choice, the number of scoops was your choice. And here again you have RS, FS. Rainbow sprinkles or fudge sauce. Wow. So I know it is really large and it's kind of spread out, but it gives you a very nice view of what your options are. Okay. So what it comes down to is, this is how you will read it. I'm going to circle it for you. So this is one sundae option. So you can go with 1 scoop vanilla with rainbow sprinkles, right? So the other one would be, let me look for a different color. The other one could be like this. One sundae option, where you could have one vanilla but with fudge sauce. And then you could go for some random option here. So that's another sundae option. Does it make sense? So you can go for 2 scoops, one flavor which is chocolate, and one topping which is rainbow sprinkles. So what you see here is the bottom row, the red row, kind of tells you all the possibilities. So it's enough that you just counted the bottom row, because that branches back in turn and it leads you back to that path, right? So it's coming from that big tree, and then these are the branches. So count these branches. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you look at the total number of possibilities for a sundae, there are 12 possibilities. Okay. So I'll say total number of possibilities for a sundae equals 12. So what does this mean? If you go back to the claim of this ice cream parlor, they said try a new one every day for 2 weeks, right? If it's 2 weeks, there are 14 days. So, but then if you look at the options, you only have 12 options. So you cannot really try a new flavor for 2 weeks. You can only try it for 12 days. So their claim actually, that slogan is actually false, right? That's what you conclude. So, so that's a nice example here. We're going to use this example for to describe upcoming concepts as well. So I want to insert a quick formula here. We just saw this formula, but I'm going to give you a formal name for this. Relative frequency method. We've seen this in chapter 2, relative frequency table. It's a similar idea, relative frequency. In relation to the whole, what does it mean? That is what a relative frequency would mean. What is this frequency? What is the number of times that occurs here? How does it relate to the number of times it occurs in total? So P of A, probability of finding an event occurring, would be the number of times. With this, just what we did above, I'm just formulating it. Number of times event A occurred divided by the total number of events. In the sample space, SS. So I'll give you an extension of the same ice cream problem. The 2 brothers in the first example decided to try the lucky sundae, where the employees of the ice cream parlor choose the sundae for them. A. What is the probability that the brothers will end up with a 2-scoop chocolate ice cream fudge sauce sundae? And B. What is the probability that they will have a sundae with strawberry ice cream? So we need to find the chance, right? The likelihood. What is the chance? What is the probability that they will end up with 2-scoop chocolate ice cream fudge sundae? So to kind of formalize this, this is my event. My event is getting a 2-scoop chocolate ice cream. I know it's hard for you to concentrate on the problem with all the yummy stuff in this problem. So that is our event. So you always can describe the event in words, right? That's how we can understand what they're talking about. But when we talk about probability of A, remember that's a number. If you go back, I just gave you the formula. It's the number of times event A occurs divided by the total number of events in the sample space. So we know that there are totally 12 possibilities, right? We just measured that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We counted it to be 12. So we got the 12. And we now need to look at the numerator. It says the number of times event A occurs. So how many options do we have for them to get 2-scoop chocolate ice cream fudge sauce? So let's go to the 2-scoop tree. So that's the 2. And then you want to go to the chocolate. And then you want to go to the fudge sauce. So you can see that your option for that is just there's only one option, right? There's no other option where you get 2 scoops and a chocolate and a fudge sauce. This is the only option. So you can clearly see that that is our option, meaning that is the only number of times. There's only one number of times that the event A can occur. So your probability is 1 out of 12. I use the traditional A. You could use L for the lucky Sunday or something like that. Right? So we're not stuck with A. It's just convenient for us. All right, let's move to B. B, what is the probability that they will have a sundae with strawberry ice cream? So I'm going to use capital B to describe this. Okay, so strawberry, getting a strawberry sundae ice cream. So for that, we have to understand that the condition does not say how many scoops. It does not even say what toppings. It only gives the flavor of the ice cream. So then we have to go back and see what are the options then for selecting that. So now our focus is only on strawberry. So I'm looking at this option strawberry here and this option strawberry. So there are 2 trees that it really leads to, right? So I have a 1 strawberry leading me to either a rainbow or a fudge option, or I could go with 2 scoops again leading me to rainbow or fudge option. So what I have then is 1, 2, 3, 4. I can count 4 options there. And that tells me that there are 4 possible outcomes. So if I were to put this in like a set notation for us, right? It's kind of hard to do that, but I'll just say 1 strawberry rainbow sprinkles, 1 strawberry fudge sauce, 2 strawberry rainbow sprinkles, and 2 scoop strawberry fudge sauce. It's kind of too much, but I hope you can see what I'm trying to do here. Right? So then you go ahead and count how many events there are, how many outcomes there are in this event. How many outcomes. So we have 4 outcomes. So then when you try to find the probability of B, you know that is 4 outcomes for the event B divided by total of 12, which then reduces to 1 over 3. So the probability of the brothers getting a sundae with strawberry ice cream is 1 over 3, 1/3. I would like to introduce the next principle, which is the fundamental counting principle. What happens here is, let's take a look at the ice cream example and assume that instead of 2 toppings, there were 20 different toppings. Right? Realistically, that's what happens, right? In places like Yogalicious and all that, they have several toppings. So if you had 20 toppings, is it even practical to draw your tree diagram with 20 options for each ice cream flavor? And again, you can imagine the ice cream flavors could be again plenty, right? Think of another 20. So it becomes quite tedious. And how do we do this without a tree diagram? Or how can we overcome the limitations of a tree diagram? That's where fundamental counting principle comes in. Okay. So it basically says multiply the total number of outcomes in the first process, second, and the third process. Okay. So if the number of outcomes in the first process, if in our example it was our scoops, right? Let that be A, but in our problem it was 2, right? We had 2 options, 1 scoop or 2 scoops. Then number of outcomes in second process. This is in general, but for our particular problem, it was the flavor, ice cream flavor. And we had to call that B. We had 2 flavors. And then the number of outcomes in a third process. And for us, it was the toppings. Yeah. So let me call it C, I'm sorry. C, and that was 2. So the fundamental counting principle, FCP, I'll just call it that for short, says just multiply A times B times C so that it gives you the total number of outcomes, to get the total number of outcomes or total possibilities. So in our problem, if we just did 2 times 2 times 2, okay, I feel like I'm missing something. Was there? We had three ice cream options. No wonder it didn't match up. So we had 3 ice cream options: vanilla, chocolate, and strawberry. Sorry about that. So I'm going to change the flavor to 3 here, and that will fix it for us. So that's going to be 3. So 2 times 3 is 6, 6 times 2 is 12, and that's what we got from our bottom row, isn't it? So we had 12 possibilities from the tree diagram, and that told us that this was the total number of possibilities for creating a sundae. And so this is a quicker process for us, isn't it? So then we'll take a look at the next example. I'm going to take you from ice creams now to pizza. Okay. A local pizza parlor claims that they have over 100 pizza options and advertise a pizza for everyone. A group of friends visit the pizza parlor to check out their menu, and they find this on the menu chart. And it says to make a pizza, each customer must select one option from each menu column. Okay, one size, one sauce, one cheese option, and one topping option. So A, are there over 100 pizza possibilities? B, what is the probability that a randomly selected pizza by the group of friends will have pepperoni on it? Okay. So you can do the tree diagram, but you notice that it's going to be tedious. So the best way is to see how many processes we have. So how many steps? We have 1, 2, 3, 4, 4 options, 4 steps to create this pizza, right? So the number of outcomes in the first process is the size, right? So I'll say 3. 3 options. For the sauce, 2 options. Cheese, 3 options. And toppings, 6 options, right? And if you use the fundamental counting principle, it makes our life so much easier. Fundamental counting principle says multiply each of their total outcomes for each column. So just to help us see this, it's going to be size times sauce, number of options under size, number of options for the sauce, times cheese, times toppings. And that comes out to be 3 times 2 times 3 times 6. If you multiply this out, you get 108. So are there over 100 pizza possibilities? Yes, we do have more than 100 pizza possibilities. B, what is the probability that a randomly selected pizza by the group of friends will have pepperoni on it? So you have to first understand what the event is, right? So let me call it as A. A is getting a pizza. I remove all the clutter, so it just means getting a pizza with pepperoni on it. So what this means is it doesn't matter the size or the sauce or the cheese. There was no specifications on that or any of those. It was just the pepperoni. So if you think of it, pepperoni is one of 6 available toppings. So if we were to draw a tree diagram, right? So for every final row, the last row of branches, right, there would be a pepperoni. So you have then, the probability would come up as 1 out of 6. Will be 1 out of 6. So if you want, you can draw the diagram to get this, or you can visualize it, which is a whole lot better. To kind of help you here, to visualize this, I just want to go ahead and kind of explain here. I did explain, but I just want to show. If you were to write this out, how would it be? So you can see that we have 108 options, right? 108 options. So I'm just going to show you how tedious it can get if you cannot process it in your mind, but if you have to see it written down, it's a little time consuming. If you have the time to do it, that is totally fine. Okay, so now I have to set up 4 of these options, right? So small, garlic, mozzarella, pepperoni. Small, garlic, mozzarella, sausage. Sausage. This is going to be tedious, I can already tell. Small, garlic, mozzarella, ham. Small, garlic, mozzarella, pineapple. Because almost pepperoni, that is pineapple. Small, garlic, mozzarella, onions. Small, garlic, mozzarella, peppers. So I just say PS for peppers. Okay. This was just the first branch, right? This came from the first tree, I could say. Right? And then, so we move to the second tree. So, anyway, this was an example for you to see how when we list it, it's going to be like that. So, you're going to have a lot of lists. And then, in fact, this goes on, and maybe your last one would be large marinara parmesan, parmesan, and then peppers. Okay. So we need to know how many there will be. Okay, you can actually figure that out. But if you were to do the tree diagram, you can imagine that you would have small, medium, large. And small would have garlic and marinara. And then garlic would have mozzarella, provolone, and parmesan. And then mozzarella will have 6 of those. Can you see what I'm trying to do? It's driving me crazy. Okay, so this, and it's not even the first tree that I finished. It's already cumbersome. There's no space, that's why. Pineapple, onion, and peppers. And then I have to repeat this whole thing for the PR, which is provolone, and then for the parmesan. And then I have to do the same thing for the marinara, right? So mozzarella, PR, par. So what we are saying is, when I try to reason out and get 1/6, what we were saying is, you just do, if it helps at all, do one branch, okay, one of it, and you can see that, oops, you went to the pepperoni, right? So, you'll get a pepperoni from there. You'll get a pepperoni from here, pepperoni from here. So you can eliminate the other choices, right? And then here too, you get a PE. So if you were to count that, okay, if you were to count that, you can see that actually speaking, and you have to do this for M and L, right? So try to see how many you'll get from the first one alone. Okay, and this is a PE. So 1, 2, 3, 4, 5, 6. I get 6 from the first one, right? 6 options. So 6 times 3, that's the same thing I'm going to get from M and from L. So 6 times 3 is 18. So if you did this, you should get 18. If you listed it out like that, if you did the tree diagram, you should get 18. A. So 18 outcomes. So if you did the P of A, it's a total number of outcomes from A, which is 18, divided by the total overall outcomes, which is 108. Simplify this, okay? 9 times 2 is 18, 9 times 2 is 12, 1/6. So you get 1/6 from doing this, okay? So I just wanted to kind of show it to you that even though it's cumbersome, you still have ways to overcome that. If you still like to do the tree diagram, make sure that you understand the process and do it for one of them, and multiply it by how many ever options you have, how many ever trees you will create from the first process. Okay. Okay. So Cynthia is looking to hire 2 new employees, and all applicants are either from Reading, Pennsylvania, or Bethlehem, Pennsylvania. So for Reading, for that city, they call it R, and for the other city, they call it B. Okay. She randomly picks 2 applicants from the entire set of applications. They're looking to hire only 2 of them, so she's randomly picking them. And the tree diagram below shows the probabilities of the different outcomes. They give us the information on the probability already, so that's good. And then, based on this diagram, what is the probability of hiring 2 employees from Bethlehem, Pennsylvania? What is the chance of hiring 2 employees from Bethlehem? So for that, again, look at your tree diagram and try to trace out the option that provides you to choose someone from Bethlehem the first round and also from Bethlehem the second round. So if you look at this R branch, you know, that is kind of ruling it out because you don't have the Bethlehem there. So then you're looking at this B, and that branches to R and B, but you want the second one also to be B, right? So the first applicant is from Bethlehem, the second applicant is also from Bethlehem. So look at the given stated probabilities and then use that to compute your probability. Okay. So the probability of getting 2 employees from Bethlehem is 7 over 11 times 6 over 10. Doesn't matter what those numbers are, we are able to use the probability information that they've given us. So that's going to be 42 over 110, which reduces to 21 out of 55. You can leave it as a fraction like this if they wanted, or you could convert it to a decimal or a percentage and go further and explain the percentage as the probability as a percentage. Here, usually, the homework problems will ask you to leave it as a simplified fraction. So you cannot use a decimal answer generally. So this is an example of how to leave it as a fractional answer. Let's now discuss about basic probability distributions. And for that, I want to define what a random variable is. Now, in math, you have heard about random variables. It's a similar concept, just that we're going to see it in terms of the experiment. So the random variable is denoted by an x, capital X. Okay, here it's case sensitive, as you've seen. Like, for instance, the size of data variables for a sample would be small n, and for a population would be capital N. So it's case sensitive. So use capital X for random variable. Small x is reserved to indicate data variables. You can say x's, all x's. Small x's, are you talking about data variables? Data values. Okay. So just say capital X. Okay. And what this means is it describes the describes the outcomes of an experiment. Of a statistical experiment. Then, because of that, it can take a set of different possible values. So let's take an example, okay? Now, think of this experiment where you're flipping a coin, right? So I'll just write here, flipping a coin. So one coin would be these outcomes, H, T, right? So if I said the random variable, okay, so if my random variable describes in this experiment, okay, if it describes the number of heads obtained in 2 coins, right? If that was how I described, then if you look at the sample space, remember we had H, HT, TH, and TT, right? So what we see is, if you were seeing it in terms of random variable and assigning values for the outcomes, and you're interested only in the heads, right? So we see that there is a possibility of getting 2 heads, 1 head in each of these cases, and 0 heads, isn't it? So then your x, random variable x, will have all these possible outcomes, 0, 1, or 2, where you're saying there can be 0 heads. When you flip 2 coins, there could be 1 head, or you could have 2 heads when you flip 2 coins, right? So we can then see that you're able to now not keep it as letters. You're able to assign a number, the random variable, because it can vary depending on how the flip happened, right? So the outcomes are described numerically in a random variable. And how do we denote it? We denote it with the letter x, but if you're trying to find the probability, okay, of that x will take one of these values, right? The capital X is all of these. So what is the probability that the value of x takes one of these? So I'll write that here. Probability of x equals x. Okay. What this means is, sometimes they will simply say P of x, which is what we've seen before. But remember, it is basically the x, capital X is all the choices, and what if it chose to be one of those x's, one of those choices, to be this, this, or this, right? So we're saying this denotes the probability that capital X, the random variable x, will take the value, rewrite that, of small x in one trial of the experiment. So I'll give you an example here. Okay, x is the number shown on a roll of a standard number cube. You know, the die, basically. So if I write P of x equals 2, what this means is, they're asking us to find the probability. This means the probability that the number cube shows 2. That's what this means. Remember again, x, capital X, has how many possibilities? 1 through 6, right? 1, 2, 3, 4, 5, or 6 if it's a die. And if we have x equals 2, we are specifically saying, well, what is the probability that the number cube shows a 2? So 2 is one of the possibilities out of the 6, isn't it? So we're going to use this idea to build probability distributions. Okay. So we have a couple of conditions there. Let's take a look at that, and then we'll go about building it. So it's a chance. What is the probability of each of these random variable values occurring, right? And so for that, we have the first condition where it says each probability P of small x, right, because it's one of those values, must be between 0 and 1. We've seen this before. No matter what it is, if it's a probability, it must be between 0 and 1. But this is how we write it, in a mathematically mature manner, where you say P of x must lie between 0 and 1, 0 and 1 included. 0 means absolutely not going to happen. 1 means absolutely going to happen. And then it says sum of all the probabilities is 1. So remember the notation we use the summation symbol, right? So the sum of all the P of x's must be 1. You'll understand this when we look at the upcoming example. So here we have a distribution, and it says, is the following a probability distribution? So recall we had those two conditions, right? That each probability must be between 0 and 1, and that the sum of these probabilities should add up to a 1. So if these two conditions satisfied, we know that it's a probability distribution. So condition number 1 is that each probability value in the table, so we have 1 over 2, that's the first one, right? That is less than 1, meaning it's between 0 and 1. Then the next value in the table is 1 over 3, that's also between 0 and 1. And the next one is 1 over 6, that's also between 0 and 1. So condition 1 is satisfied. Condition 2 says sum of the probabilities must be equal to 1. So half plus 1 over 3 plus 1 over 6. You have to check if it is equal to 1. So for that, of course, use the LCD, right? So that will give you 3 over 6 plus 2 over 6 plus 1 over 6. Use LCD to convert all your denominators to be the same, because you can only do it with like or common denominators. And that will now you're free to add the numerators freely. So 3 plus 2 plus 1 is 6. 6 over 6 is 1. So the second condition is also satisfied. So you can say yes, it is a probability distribution. Okay. What if you were given partial information and asked to create a probability distribution table? So here's an example. A news program reports that 46% of the population are in favor of a certain issue and 48% are against the issue. Create the corresponding probability distribution table. Now, right away, if you know the percentages are your probabilities, right? Usually. But here they're talking about the proportion that are in favor or that are against. So if you look at this 46% and the 48%, right? They were in favor. So these people said yes. This percentage of people said no. If you see that if you add these two, it only takes you up to a 94%, right? So to build a probability distribution, they must add up to 100%, because when they say the sum should be 1, 1 is the same as 100%. Therefore, it is a common practice, although it's a common practice to report yes and no only, here we will include the undecided category. Okay. So what is the undecided category then? That's the remaining ones, right? You need 100%. You got 94% of response. So the undecided should be the 6% of the population. Okay. So if you were to build a probability distribution based on this, you have the random variable column and the P of x column, where it's for each x. So for those who said yes, it would be 46%, which is, remember, it has to be written in a decimal form so that you can judge if it's between 0 and 1. No would be 48%, which is 0.48. And then undecided would be 6%, which is 0.06. Watch out for that. And then if you did add these three, you'll get a 1. Individually, they are each less than between 0 and 1. So you have built a probability distribution that is looking good. Okay. Now, if you had a distribution, this is what you created, so we're careful about the conditions. Sometimes you can, just to confuse you or just to test you, they can give you information like a probability that is negative 1/4. Okay, don't be alarmed because you can never have a probability that is negative. So again, don't think that something is wrong at your end. It's just that they've presented the question like that with an incorrect probability. So it cannot be a probability distribution, even if one of the probabilities doesn't work. Okay. And let's say if you are given 0, is that okay? If the probability, say undecided, was 0, instead of say we got 100% from just the yes and the no. 0 is totally fine because, in your probability, it can accept 0 and 1 inclusive. So that is fine. Negative probabilities or probabilities that are above 1 are the ones that won't work. Here comes our last example for this lecture. A student randomly selects classmates from their local community college, and they ask each how many siblings he or she has. The table below summarizes the data. Construct a probability distribution. What they gave us here is a frequency distribution. Can you recognize that? You have the frequency column, right? So what is given to us is a frequency distribution. And we need to create a probability distribution. So for that, I'm going to add another column because remember again, if you recall, we saw the formula to find the probability to be relative frequency formula. And previously in chapter 2, we learned about relative frequency table. So relative frequency and probability are the same. Does it make sense? So let me write that here. Relative frequency is the same as the probability that we're looking here. So go ahead and build another one. I'll just use the space. I'm going to call it P of X. Okay. So that, you know what, actually it's too small for me, but I'll just try to write as best as I can. Now for relative frequency, we have to have the total of this column, right? So get your total, and that will be 40. Summation of F will be 40. Okay. So relative frequency says take the current frequency in that class and divide it by 40. Take the next one, 17, and divide it by 40, and so on. So because it's too restrictive there, I'm going to just do the F and the P of X alone, so it's easy for us to see and a little bigger. And here we got the total as 50, right? So the P of X would be 8 over 50, which is 0.2. Use your calculator to compute that. 17 over 50 is 0.425. 11 over 50 is 0.275. 3 over 50 is 0.075. 1 over 50 is 0.025. Now, of course, each of them are less than 1, between 0 and 1. If you added these, you'll get a 1. And so you can see very, very clearly that you can build a probability by using the relative frequency formula. So I just want to write here that this is the same as relative frequency, which says take the frequency for that particular row divided by total frequency, which is the same as take the number of outcomes and divide it by the total number of outcomes. That's the formula we learned here in probability. So we were able to build a frequency distribution from a we could build a probability distribution from a frequency distribution, right? So I hope that helps here. And with that, we wind up this lecture here. And we will continue with Chapter 3 topics in the upcoming lecture. See you soon.